GOC lecture. Now let's start our GOC lecture. According to this, let's discuss some example. In previous we discussed about what is localized and what is delocalized. So here are some examples. This nitrogen, it has lone pair and it will go here and this will be go here, so it is delocalized, not localized. It is also here, electron density go from here to here, lone pair here, and this is also here localized. It is delocalized, it is also delocalized, it is also delocalized, it is also delocalized, this is also delocalized, and this is also delocalized, this is also delocalized. Example of delocalized: here lone pair is present, so it will donate the electron density from here and this will go here, so it is also delocalized. Here the electron density comes from here and this benzene ring here, and this is the resonating structure can be formed in this molecule, so it is also delocalized. Same thing can be said about the oxygen. It will donate here and this will go here and all the way from here, so it is also delocalized. In this molecule a lone pair is present and just a double bond is present here, so it is a localized lone pair, so there is no resonating structure can be formed, so it is localized. This is also localized because it is the sp3 carbon present here, and there is no motivation because bond is here same, so this is also localized, and this is also localized, it is also localized because there is nothing that the sulfur electron can go. So here are some examples in which we can see this is an example of anion, a negative charge species. So we need to know whether this is localized or delocalized. So here electron density can be go, this negative charge go from here to here and here to here and all that, here to here and here to here, so this is a delocalized electron. It is also delocalized electron, it is also delocalized, and this is also delocalized, and this has also delocalized, and this is localized because a double bond is present, so it cannot move, so it is localized anion. Here a lone pair is present and an anion is present, so it is localized because of the double bond, and here it is delocalized because there is nothing to stop, this will go here and here, so this is delocalized. This is also an example in which delocalization can be seen. This is also delocalized, and this is an important example. CH2 negative charge is connected with single bond to PPH3, so we know that in PPH3 an empty p orbital is present, so the electron density of this anion will transfer from here to this p orbital, so delocalized, it is also delocalized electron. Here this negative charge cannot go to this NH3 because it do not have an empty p orbital, so it is localized. Which same can be speak about this sulfur positive and 2 methyl group, so it has an empty d orbital, so transfer of this charge can be seen here, so it is also delocalized electron. Same can be said about the CH2 N plus and double bond oxygen, so due to presence of this double bond oxygen in N plus, so electron density can be go here and this negative charge can become here, resonating structure can be formed. So another example of this is can be said about this, it is this negative charge can go from here to the empty d orbital of silicon, so it is also delocalized electron anion. Here also a negative charge can be transferred all the way from here to oxygen, and this negative charge anion can also go from here, so it is also delocalized. These negative charge cannot go anywhere because there is sp3 carbon to sp3 carbon, so no bonds are present, so it is localized. And here this chlorine this negative charge is present here and this double bond is present, so it is localized. Now let's talk about the very important topic in which we talk about the linear conjugation and cross conjugation. So what is linear conjugation and what is cross conjugation? We will discuss this further down. So what is conjugation? Conjugation is the alternation of single and double bond, as we have studied in previous classes. Conjugation. So as you can see, this is a linear conjugation example. Here a negative charge is negative anion is present, so electron density will come here, and this type of motion is seen here. So resonating structure can be formed, and same applied with this. If a double bond is present here, so this is positive charge, so to fill this, the electron density come from here and fill this bond here and here. So this type of linear, this is called linear conjugation, and this is an example of cross conjugation. So that means the electron density come all the way here and here, and it can also come from here and here. So the two-way conjugation can be possible here, both side conjugation. So this is called cross conjugation. There is another example in which this and this. So if a positive charge is present here, or the CS2 bond, so the electron density can come here and it can also be go here. So the electron density of this bond can come here and here. The two places that can be go. So these are the example of cross conjugation. And there is an important example that we used to study in our organic classes. So this is the example. So it is also an example of cross conjugation. This electron density can go here and it can also be go here. Two ways can be possible. So the application of this is, we can speak about the stability of anion. So let's take an example. This is a negative charge, and this is an example. So we need to tell which molecule is more stable. So there is a negative charge, so it can go here and here, and it can also be go here and here. So the dispersion of negative charge is more in B as compared to A, because here only one directional is present. So B is more stable. Compared to A. So now we are going to discuss an important topic, which is resonating structure and their stability. So resonating structure can be made of, this is an example, this is a ring. So we need to know whether how many resonating structure can be formed in this molecule. So first, this electron will go here and this is go from here to here. So oxygen, hydrogen, this will become double bond, and a negative charge will be here. So this is first resonating structure. Then this negative charge will go here and this will go to the here. So this oxygen, the positive charge will come here because the electron density go from here to here. So oxygen with positive charge, double bond, a negative charge will be placed here and a double bond will form here in this direction. Now let's make another resonating structure. So here what happened is, this negative electron density go here and this will go from here to here. So negative charge can be found here, a double bond can form here, and this is oxygen and hydrogen, and positive charge can be. So these are the three resonating structure. After that, this will go here, and this bond will go into the back formation, and it forms a similar structure, or a fifth resonating structure, which is equal to oxygen, hydrogen, a single bond, and the position of bond which is here can be transferred after doing a resonance. Well, to know the stability of these resonating structure, we use a rule called OLS rule, according to which O represent the octet. First point, which is octet must be complete. That means, let's count electron. Let's make this hydrogen. So here we know that oxygen have 6 or 8 electrons, 6 electrons. So 2 plus 2, 4, 5, 6, 7, 8. So 8, which is an octet, must octet complete. So it has a. So this OLS rule of resonating stability is very important, and it is applied only through this sequence. So sequence is important here. We cannot skip the sequence first we need to check whether all these structure have the octet must have complete from all these structure. So everyone has octet complete, as we can count just like that. And hydrogen with positive charge, and 1 2 bond from here, 1 2 3 4 5 6 and 7 8, a lone pair is also present. So this has an octet complete structure. And the second step for this is neutral structure will be more stabilized as compared to charged structure. So these are the neutral structure. First, this is second, this is third, this is fourth, and this is fifth. So as you can see, the first and fifth structure have neutral structure. So if we do the stability order here, so first, which is approximately equal to fifth, will be ahead of the other. Now the next is more electronegative पे negative charge stable होता है. So this is not applicable because there is no negative charge or electronegative atom present. So now let's get to the fourth point, which is separation. The charge separation, in which when an opposite charge is present, so the distance between the opposite charge is minimum, is preferred. So as you can see, a positive charge is here and a negative charge is here. So this is the least distance, and same can be said about this is also least distance. So as compared to this third structure, which has a long distance, this positive is here and this negative is all the way from here. So the second and fourth is similar as compared to third. So this is the stability order of that molecule. Now let's discuss the important topic, which is resonance. So what is the resonance? Resonance is the condition. So there are two types of resonance, plus R and minus R. So plus R are our electron donating group. These can be NH2, SR2, which have lone pairs, so this can donate electron. OH, and of fluorine, which is in electronegative groups, fluorine negative, chlorine negative, or oxygen negative, nitrogen negative, carbon negative, or sulfur negative. This can be an electron donating group, so plus R can be seen, or plus positive resonance. And in minus R group, an electron withdrawing group are present. So electron withdrawing groups such as NO2, which take electron density away from the ring, or the CN group, it's triple bond, so this will also take electron density from the ring. Or any carbonyl group, just C double bond O, OH, or aldehyde COOH, etc. So in resonance, when plus R, what is happening here is when a ring is present and an electron donating group is present, just like oxygen with negative charge, so the electron density of the ring will increase. And in minus R group, when a ring is present and if a minus R group is present, just like C or double bond oxygen, or it can be X and halogens, so this will take electron density and put them into this perspective. So this type of resonance is called negative resonance. So there are some application of resonance in which we discuss about the stability of carbocation, stability of carboanion, and acidity. So let's take an example of stability of carbocation. So we know that it is a carbocation. So to make this carbocation, we need electron donating group, just like this. This is an electron donating group which is donate this electron density and go all the way from here to here. So this is plus R effect. This NH2 group is also have lone pair, it will also donate electron, so it is also a plus R effect. So this CH3, we know that it is also donating group, but it do not have any lone pair of electrons, so plus R cannot be possible here. So it only donate from plus H, hyperconjugation, because it has alpha hydrogen and these are alpha carbon alpha hydrogens are present, so plus H and then plus I. So this is plus I, plus H and plus I can be possible for CH3 group for this carbocation, and this hydrogen will not affect anything, it is a neutral molecule. So and the Cl group, which is electron withdrawing group, it is an electron withdrawing group, so it will make this it is also very poor and make it even more poorer. So this is an minus I effect, because it is not a minus R plus R effect. Why? Because halogen, which is attached like this, have more minus I priority or the dominant as compared to plus R. So we only considered minus I, or we do not consider plus R here. So according to which, if it take this as 1, 2, 3, 4 and 5, so the order of stability is, this is making as compared to these two, the B, this is the more stronger donating group, so second will be in the first position, then first, then the C third, because it is donating from plus H. So after resonating hyperconjugation, if we talk about the priority order, so priority order will be resonance, then hyperconjugation, and then inductive effect. So, and there is neutral, which is 4, and in last, which is taking the electron density away from the ring, so this will be in the last position. So this will be the stability order of the molecules. Now let's discuss about the next effect, which is mesomeric effect. So here we can see it's a direct donation. It can be of two types, plus M and another is minus M. So what is the plus M effect? So we can understand this with taking an example. It is a type of direct donation from lone pair to carbon positive cation with an orbital of empty p orbital. So the donation of lone pair from nitrogen, or maybe it can be oxygen lone pair or sulfur lone pair, directly from lone pair to the empty p orbital, and the carbocation is called mesomeric effect, plus m effect. It is called plus m effect. And in case of minus m effect, when and cation is connected to an empty p orbital or the empty d orbital, when an anionic charge will go from negative charge to the electron density of empty d orbital of silicon or any other group of group 13 to group 17, just like silicon, aluminum, sulfur and phosphorus or chlorine. So these are called minus m effect or negative mesomeric effect or positive mesomeric effect. Here electron density from the lone pair is go from here to the empty p orbital. So these are also helpful for determining the stability of carbocation, carboanion, and acidity and basicity of the molecule. So let's take an example of a mesomeric effect or example in which we need to calculate the acidity order, who is the good acid. So the example is CHCl3 or CHF3. So we know that to understand whether the compound is acidic or not, an hydrogen is removed and a cation is formed. So carbon with negative charge and these three chlorines are present here. So and according to this molecule, here also a carbon, hydrogen and three fluorines are present here. So it also have negative charge if this hydrogen will go and taking plus charge with it. So this carbon get negative charge, and we know that chlorine has an empty d orbital. So this is also have empty d orbital. So mesomeric effect can be possible here. Mesomeric effect cannot be possible in fluorine molecule. So it will only take electron density from minus I effect as it is dominant effect. So we know that, and it also chlorine will also take from minus I and it also take from minus M effect. So this, as we know, this mesomeric is dominant over resonance and its dominance over hyperconjugation and its dominant inductive effect. So these are the priority order in which we need to follow. So this mesomeric effect is more stable as compared to these molecules. So acidity is directly proportional to the stability of negative charge or this carbocation ki stability ke. Then this is more acidic as compared to this. There is another example of acidity order. Acidity order is directly proportional to mesomeric effect. So let's take another example. A 5-membered ring with 2 sulfurs and a hydrogen. 1 sulfur and a hydrogen and nothing and a hydrogen. So we know that for the acidity, the hydrogen is removed and a negative charge will come here, and hydrogen is removed, negative charge will come here, hydrogen is removed and negative charge will come here. So we know that due to presence of empty p orbital, this negative charge is more stable here. So here it is more stable, but here 2 mesomeric effect is present and here 1 mesomeric effect is present. 1 plus M effect is present, and here nothing is present for the stability. So the stability order of this is, if it is B, if it is C, then A, B and C will be the stability order of acidity. Let's take another example in here for basicity order. We have to calculate the basicity order of this group, and a methyl group is here and methyl group is here and a methyl group is here, and this has a lone pair, and we compare this with nitrogen lone pair and a SiMe3 group and a SiMe3 group and a SiMe3 group. So here, to get the basicity, we know that if a hydrogen, if a H plus will come here and came here to get attacked, so this lone pair of nitrogen is not available to give donation, because it is going from this empty p orbital of this silicon. So it can be here one time, here or here, so it is most likely to be not found. It is not more basic, and this is more basic. Why? Because this hydrogen, this methyl group will get here and produce minus I effect from this direction. So it will increase this nitrogen lone electron density, and it is more easily come to this hydrogen ion. So it is more basic as compared to this. So it is less basic and this is more basic. So the order of basicity is like this.